Human blood functions as a highly pressurized fluid connective tissue, constantly surging through the body with an intense rhythmic force. In 1628, physician William Harvey proved that this tissue flows through a continuous, closed-loop system. Driving this closed system requires a standard operational pressure of 120/80 millimeters of mercury. We measure this mechanical force using a sphygmomanometer, an instrument consisting of an inflatable cuff and a pressure-detecting gauge. A healthy adult maintains a total systemic volume of 5 to 6 liters, accounting for 7 to 8% of their total body weight. This physiological volume varies slightly by biological sex. Females typically carry about half a liter less than males. Survival depends on maintaining a strict chemical environment within this closed loop, specifically a slightly alkaline pH of 7.4. This animation shows what happens when we place this tissue in a centrifuge. The shear force divides it into two distinct parts: a clear plasma matrix, making up 55% of the volume, and a cellular payload, making up the remaining 45%. This strict physical and chemical baseline allows a single fluid to act as a transport matrix, a gas exchange system, and a structural organ. This diagram shows the top fraction of the centrifuged file. This is plasma, accounting for 55% of total blood volume. Plasma is 90 to 92% water, acting as the ultimate systemic solvent, transporting dissolved nutrients and hormones to organs that require them. This liquid faces an internal physical contradiction. It must never solidify inside the veins, yet it must instantly turn solid upon an external injury. To enforce continuous internal flow, the body relies on heparin. Heparin is an anticoagulant compound that actively prevents the blood from coagulating while it is still inside the circulatory system. Suspended silently alongside it is an opposing force, fibrinogen. Fibrinogen is a latent blood clotting protein ready to deploy the moment a vessel ruptures. In a laboratory setting, if you systematically remove this fibrinogen from the fluid, the remaining liquid is classified strictly as serum. Below that chemical arena sits the cellular payload, comprising the remaining 45% of the blood volume. This diagram illustrates the strict mathematical hierarchy governing the cellular fraction. For every one white blood cell, there are exactly 40 platelets and 600 red blood cells. Plasma operates as a highly volatile chemical arena, where the constant threat of systemic coagulation is suppressed by a perfect balance of opposing proteins. The dominant cell type in that ratio is the erythrocyte, or red blood cell. In an adult, these are manufactured almost entirely within the bone marrow. The only developmental exception occurs during the embryonic stage, where the liver and spleen temporarily take on the responsibility of manufacturing them. To maximize internal volume, mammalian red blood cells execute a radical evolutionary trade-off. As they mature, they permanently eject their entire nucleus. There are only two distinct biological anomalies to this enucleation rule: camels and llamas, both of which retain their cell nuclei. Internal space clears to pack in hemoglobin. Built around essential iron atom, it gives blood its red color and transports oxygen and carbon dioxide. However, a dangerously high binding affinity for carbon monoxide can permanently block other gases from attaching. Because they lack a nucleus, these cells cannot repair themselves. They operate on a strict finite life cycle of between 20 and 120 days. The logistics of managing this life cycle fall entirely on a single organ, the spleen. The spleen plays a dual paradoxical role. It acts as the systemic blood bank, holding emergency reserves, while simultaneously serving as the graveyard where old, damaged cells are dismantled. Erythrocyte production is highly responsive to environmental demands. When the body enters a sleep state, the active cell count drops by about 5%. Contrast that resting state with extreme environmental stress, such as traveling to high-altitude environments. At elevations around 4,200 meters, extreme oxygen scarcity forces the body to rapidly adapt, increasing erythrocyte production by up to 30%. The red blood cell acts as a stripped-down, disposable cargo drone. It is constantly mass-produced and destroyed to perfectly scale with the density of oxygen in the surrounding environment. We then look at the rarest cells in that ratio, leukocytes, or white blood cells. These are the primary agents of the human immune system. These defenders operate at physical extremes. Monocytes are the largest of the leukocytes, while lymphocytes are horizontal ruler connects them, highlighting the extreme size difference within the leukocyte family. Specific pathogens have evolved to exploit this exact defense network. The HIV virus surgically targets and destroys the T4 lymphocyte, neutralizing the immune response. The middle tier of the cellular ratio consists of thrombocytes, or platelets, which are responsible for rapid mechanical repair. Just as HIV targets leukocytes, the dengue virus specifically targets and decimates platelet populations, systematically stripping the blood of its ability to seal wounds. This diagram shows the external clotting cascade. This emergency physiological response averages 2 to 8 minutes from the moment of injury. Creating this structural seal requires platelets to physically interact with fibrinogen, prothrombin, vitamin K, and calcium, forming a solid matrix over the breach. While red blood cells sustain life via gas exchange, the leukocytes and thrombocytes operate as automated damage control. They constantly patrol the closed loop for both biological invaders and structural ruptures. Understanding the internal mechanics of a single human's blood reveals exactly how difficult it is to mix two different circulatory systems. The strict genetic rules governing blood exchange were formalized with the ABO blood group system, discovered and categorized by Carl Landsteiner in 1901. The system was finalized in 1902 when De Castello and Sturley discovered the final AB group. Blood types are defined by geometric antigen structures protruding from the erythrocyte membrane. Antigens trigger immune responses when recognized as foreign. Type O negative, the universal donor, is given to anyone. With a completely smooth surface, it remains effectively invisible to a recipient's immune system. Conversely, the universal recipient, AB positive, can accept any blood type. Its native plasma completely lacks the defensive antibodies required to attack new cells. The final critical genetic variable in blood compatibility is the Rh factor, discovered in 1940. The Rh designation is derived directly from their initial test subjects, the rhesus monkey. This specific factor dictates extreme consequences in human reproduction, specifically when an Rh-positive father and an Rh-negative mother conceive a child. This genetic combination creates an immunological conflict called erythroblastosis fetalis. Erythroblastosis fetalis is a fatal condition where the mother's immune system recognizes the fetus's Rh-positive blood as a foreign pathogen and actively attacks it. Blood is a highly individualized, genetically guarded tissue where microscopic surface geometry dictates systemic flow, interhuman compatibility, and ultimate reproductive viability.